Hello and welcome. Last section in this chapter, section 6.3, differential equations, and we will study more cases where we can use separation of variables. So the objectives are to recognize and solve differential equations that can be solved by separation of variables, and use differential equations to model and solve applied problems. We'll see in particular two problems that are rather complex, and we'll go through the solution together. First example looks very difficult. Solve the differential equation that is given here using separation of variables. It looks like an awful expression here. Actually, it's not that bad. We can separate variables by dividing by 1 plus y squared. So we move the 1 plus y squared to the other side, and we can bring the dx on the right side. So it's easy to separate variables in this exercise. Here the x's, here the y's. So we have one expression that is multiplied by dy, and we have one expression that is multiplied by dx. This is separation of variables. And these two expressions are actually not too hard to integrate. You might not remember this one, but the integral of 1 over 1 plus y squared is actually the inverse tangent. And here, 2x times e to the x squared, you might recognize that it's actually the derivative of e to the x squared. Because if we differentiate e to the x squared, it will be e to the x squared times the inside derivative, so times the derivative of x squared, which is 2x. From here, if we want to solve for y explicitly, y is equal to tangent of e to the x squared plus c. So sometimes, even in very simple situations, it's not possible to separate the variables. Here is an example: y prime equals x plus y. You can try if you want. Dy dx equals x plus y. You won't be able to have one expression in y multiplied by dy on one side and one expression in x multiplied by dx on the other. In these cases, we just need to use more complex techniques that are not part of AP Calculus AB. It's possible to solve differential equations like that, but it's not part of the curriculum. Find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared at all points x, y. If the slope is y over x squared, it means the derivative is y over x squared. This is what I write here. The derivative dy dx equals y over x squared. We can separate the variables. So 1 over y dy equals 1 over x squared dx. The integral of 1 over y dy is ln of y. The integral of 1 over x squared dx, don't start thinking it's ln of x squared or something. This is simply x to the power of negative 2, so we can just use the rules for x to the power of n. So we set up our integrals, and ln of the absolute value of y equals negative 1 over x plus c. Therefore, the absolute value of y equals e to the negative 1 over x plus c. And now we'll observe something that is quite technical. The differential equation that is given is undefined at x equals 0. So if we look here, dy dx equals y over x squared, it's undefined at x equals 0. That means, if you look at the graph, that there is a hole or something at x equals 0, and that must restrict y to the positive values. Our y is positive, y equals 3 in our particular solutions, so because of this hole we don't cross to the other side. We may feel that there is a logical continuation here. The curve is going to go like this maybe, or the curve might be going like that, but when we work with differential equations we absolutely have to stop when there's a hole or when there's an asymptote. So the solution to an equation, a differential equation like that, is always a continuous function. What that means in our case is that y is always going to be positive, so we can get rid of the absolute value. We don't care, we won't have negative values for y, therefore we can write y equals e to the negative x, negative 1 over x plus c. Most of the job is done now, we just need to use the 0.13 to find the particular solution. We can bring the plus c in front, y equals capital C times e to the negative 1 over x, and then solve for our particular solution. So x equals 1, y equals 3, 3 equals capital C times e to the negative 1, which is 1 over e, and therefore c equals 3e. So finally, my particular solution to this differential equation is y equals 3e times e to the negative 1 over x. E is actually e power 1, so we could use rules for exponents to bring these two parts together. It would be 3 times e to the x minus 1 over x. But either of these two answers is perfectly correct. Example 2 is quite complex again. Let's read the question first. During a chemical reaction, substance A is converted into substance B at a rate that is proportional to the square of the amount of A. When t equals 0, so originally 60 grams of A are present, and after 1 hour only 10 grams of A remains unconverted. How much of A is present after 2 hours? So when t equals 0 there's 60 grams, after 1 hour there's 10 grams. How much is there after 2 hours? Obviously there's going to be less than 10 grams. We have 60 grams of A, they are being converted into another substance, so A is decreasing. We had 60, then 10, and now we're going to have less than 10. What we see is that substance A is converted into substance B at a rate. So when you see rate, it must make you think you can set up a differential equation, dy dt. The rate is proportional to the square of the amount of A. I decided to call the amount of A y. You could even call it d capital A if you wanted. I just said dy, so y is the amount of my substance A, and the rate at which this changes is proportional to the square of the amount of A. Now that means at the beginning this rate is going to be very large, because when it's proportional to A, which is 60, it's a large number, so the rate is going to be large. Later on, when A decreases, like when A is only 10 grams, this is going to be much smaller, so the rate is going to be smaller. So from 60 gram it's going to decrease quickly, but then it's going to gradually slow down, and after it reaches 10 grams it won't decrease as fast. The second thing we can talk about already is that the constant k has to be a negative number because substance A is decreasing, so we have to have a rate that is negative. Alright, so let's separate variables. We send the y squared to the other side by dividing by y squared, and we have dt that we can bring to the right. So as you can observe here, we don't have any t, but the integral of k dt is easy to integrate. You could bring k to the left side, it doesn't matter, and just have dt alone here, but it's rather convenient to keep it rather than have a 1 over k on the left side. Alright, so I skipped the step where I show the integral signs here, but imagine it's the integral of dy over y squared equals the integral of k dt. So negative 1 over y equals k times t plus c, which yields y equals negative 1 over kt plus c. What we notice here is that we have two constants, k, because we knew the rate was proportional to something, so k was here originally, and then we have another constant. It's our constant of integration. Once we've integrated, another constant appear. Well, it's fine because we have two information. We know that when t equals 0, y equals 60. We also know that when t equals 1, y equals 10. So usually when we have two information, it's enough to find two unknowns. At t equals 0, y equals 60. Let's plug these numbers in. Since t equals 0, if you look here, 60 equals negative 1 over, this whole thing disappears, so just negative 1 over c. 60 equals negative 1 over c, and therefore c equals negative 1 over 60. That's great. We managed to find one of the unknowns immediately. In some cases we would have had two equations with two unknowns and we would have had to solve them together. Here, nothing of that. We can find one unknown right away, and we are going to use it to find the other one. So at t equals 1, y equals 10. This is our other information, and if I plug that in the equation, 10 equals negative 1 over k times 1 plus c. So k times 1 plus the value c that I found already. I'm going to substitute c right away, and I get an equation where I only need to find k. So that's algebra. We're going to multiply by k minus 1 over 60. So this whole thing here, we multiply by that on both sides. Therefore, 10k minus 1 over 6 equals negative 1. We add 1 over 6. It's a little bizarre when we have negative numbers everywhere, so be careful. 10k equals negative 5 over 6. And finally, by dividing by 10, you can cancel out 5 if you want, so you have 2k equals negative 1 over 6. Eventually, k equals negative 1 over 12. Alright, so we had a general solution. We found c, we found k. We can put all of that together. Y equals negative 1 over negative 12t minus 1 over 60. We can work with that a little bit. First, notice how we have negative signs everywhere, so we could already change that to y equals positive 1 over positive 1 over 12t plus 1 over 60. We're also going to multiply by 60 at the numerator, multiply by 60 at the denominator, and suddenly the equation becomes much, much easier to read. So what I did from here to there is multiply by negative 60. 60 divided by 5t plus 1. So finally we have a function that gives us the amount of substance A at any time t. So let's see how much of A we have after 2 hours. We plug in t equal 2, y equals 60 over 5 times 2, 10, plus 1, and we get 5.454 grams, which you can round at 5.455 grams. This is rounding, this is truncating, both are okay. So there we are. What were the objectives today? To recognize and solve differential equations that can be solved by separation of variables. So even sometimes things that look complex are not that complex because we can separate variables. And then use differential equations to model and solve applied problems. So set up a differential equation by reading carefully here. The rate is proportional to the square of the amount